Because waves and wind are the primary movers and shakers at the coastline, the shoreline, the shore, the coast, we have to take a look at them. So if you look at this diagram, you can see what is identified as the crest, which is right here. This is the up bulge, and right here, the other up bulge of the passing wave. Notice that in this case, the wave is going from right to left. Okay. Then the trough is the depression between crests, which is this area right here. Okay, so we're halfway through the anatomy of the wave. The wave height is the vertical distance right here between the trough and the crest. This is always measured on the back side of the wave, because as the wave comes in and it begins to bulge upwards, the face is made by depressing the sea level in front of the wave. And then the wavelength is the horizontal distance from one crest to the next, succeeding crests, of course, okay? So waves are created by wind. What happens is this: as winds are blowing along the surface of the ocean water acts as a frictional agent. What that does is it slows down the wind because of that friction. Now, the energy that is the wind doesn't disappear. What happens is the energy is transferred from the atmosphere into the water in the form of wave energy. So all that happens is that energy comes out of the atmosphere as the wind is blowing along. Because of friction, the wind slows down, and that slowing down is just a matter of the energy being taken out of the air and put into the water. That's what slows the wind down, and of course that's what creates the wave that is then transmitted through the water. Wave energy is then transferred over great distances through the water. So what's happening, once again, is energy is coming out of the atmosphere, it's transferred into the water, and then the wave energy passes through the water. I want you to understand this part of it. The water is a conduit through which the energy passes, but the water itself is not actually moving. It's the energy that's moving. It's a little bit like this. If you have a light switch wherever you are and you flip on the light switch, here's what does not happen. The copper molecules that are at the light switch do not transfer themselves and move along to the light and then illuminate the light. What happens is the electricity, which is the energy, passes through the copper wire to the light and illuminates the light. In other words, the copper acts as the conduit through which the energy passes. In the case of waves, this is the same thing with what's happening with the water. And that is that the waves are energy passing through the water. The water is nothing more than a conduit through which the energy passes. And the water molecules actually move kind of up and down. They're actually a little bit circular, but they move up and down as the energy passes through them rather than horizontally. So as the wave passes by, just envision, here comes the crest passes by, and now the trough passes by, and now the next crest passes by. That's just energy passing through the water molecules. The water molecules are just moving up and down, but the energy is passing through them, just like the electricity going through copper wires. The way a wave is formed is like this, okay? As in what we see at the coastline. The energy of a wave is transmitted to a depth that's equal to 1/2 of one wave length. Below that depth, there's negligible movement of the water related to the passing wave. Interestingly enough, my father was on a submarine up until the first part of World War II. And he was actually at Pearl Harbor when it was attacked, and he was on a dry docked submarine called the Narwhal at that time. And I remember talking to my father about this. My father was not a person who would explain really much of anything. And I would ask him, when I'd be watching these movies about World War II of these ships out in the middle of the ocean, the waves crashing over the top of them during a typhoon or a hurricane, I'd say, what do you do when you're on a submarine and there's all that action? And my father said to me, dive. That was it. Later on, when I took this class, I understood what he meant, which is that if you dive down below a depth that's equal to 1/2 one wavelength, the turbulence from the storm is not going to be felt because all the energy is superficial in the ocean. Take a look at this picture. You can see the wavelengths out there. You can see that wave out in the distance over here where it's beginning to kind of crest up as we know a wave, the thing it's rideable. But if you look out in the distance, you can see that there's other waves out here. Because what's happening is right in here, the depth of the water is equaling 1/2 of one wave length. So I made this diagram for you. Let's take a look at it. You can see that there is this blue arrow. The blue arrow right here is pointing the movement of the wave energy towards the shoreline. This is the offshore environment, the landscape, in other words, land. And then right there is the shoreline, the coastline, the shore, right? Where the dynamic interface between the land and the sea and the atmosphere, for that matter, exists. So this is right where the water is coming into contact with the land and the land is coming in contact with the water. That red line I just put on there represents a depth in the water that's equal to 1/2 of one wave length. So what happens is out here in the open ocean, the depth of the water is greater than 1/2 of one wave length, okay? However, at that point where the yellow arrow is that I just put onto the diagram, at that point, the depth of the water now is equal to 1/2 of one wavelength. When the depth of the water is equal to 1/2 one wavelength, several things are going to happen. First of all, the energy that's being transmitted through the water in the form of the wave is going to begin to have friction with the land, which then slows the wave down. The wave is then going to be pressed into a smaller space. So if the green arrow represents the wave that's passing through the water, and this is out in the open ocean where you see the green arrow, okay, it's not in contact with the surface of the land, with the land area at all. So there's no real friction with the land. But at this point where the yellow arrow is at and the green arrow is now at that point, the depth of the water is equal to 1/2 of one wavelength. At that moment, there's going to be friction between the wave and the land. That's going to slow the wave down. And as you can see, as we move towards the shoreline over here, what's going to happen is the wave is going to be pressed into a smaller and smaller area. Of course, the wave does not want that to happen. And what that does is it does this. It forces the wave to press up against the land and up against the air. Obviously, the atmosphere is a more fluid body and more pliable than the land is. Because of that, the wave, what we see as a wave from the shoreline, begins to build upwards because the wave energy is pushed up into the atmosphere because it's a more pliable agent than the land is. It's pressing down on the land also, but it's pressing up into the air, which causes that water to bulge upwards and rise. Then the forward momentum of the wave is carried towards the coastline, and that's what causes the wave to crest over and then smash down. And of course, there's drag with the land on the bottom part of the wave, which slows the movement of that part of the wave that allows this forward push and then the wave to crest up and break over onto the land like this.